So let us start. So what we saw last time was that we got this global structure of the curved space-time. So it's again mathematical picture. It's a maximal extension of the space-time that we write up here. And basically, we use this coordinates which go in, and therefore these are the v coordinates using the Finkelstein v coordinates. Then we cover this region up here. And in Schwarzschild space-time, when you go across the horizon, then you are run into a space-like singularity. But in the curved space-time, there is another inner horizon on which there's another inner horizon, and then the statement is that the singularity is at r equal to 0 up here. And I think last time I might have written here theta equal to 0, and this really, if you see singularities, and the singularity is really at r equal to 0 and z equal to 0, so that will correspond to theta equal to pi by 2 and not 0. So this really is pi equal to pi by 2, and some phi equal to phi naught. So that is the picture that we have. But again, this is the maximal extension. Mathematically, this is useful for some considerations involving quantum field theory and black hole backgrounds and such conceptual issues. This picture is important. But in the physical gravitational collapse or formation of a black hole, we won't get all these other regions. As I mentioned last time, the inner horizon is really unstable. If you put a curved space-time and put a perturbation on a space-like OG surface up here, then in fact it will pile up on that inner horizon, and therefore, in fact, the rest of the structure up here is very unstable. In other words, it is very peculiar to the exact curved space-time. It would not be shared by space-times which are near curved space-time, and therefore we really don't trust what happens up here on the other picture. The other thing that we saw last time, or we began to see last time, is the emergence of the ergo region, and that is where we ended. So this is the part which is the curved space-time, curved black hole, and interplay between geometry and physics. And I think all of you have taken quantum mechanics, and there you see interplay between kind of the Hilbert space theory or analysis or operator algebras and quantum mechanics, right? There is a translation between observables and self-adjoint operators, and Hilbert space inner product has a direct meaning, and you extract physics out of this mathematical structure. And the same thing is true in general relativity. It is really we're extracting the physics out of the geometry of space-time. And so what we saw last time was that if I looked at the form of the metric, then in fact, if I come out from by infinity, so this x, y, z are the Churchill coordinates, which actually cover this patch of space-time. This patch of space-time up here, it goes all the way inside this patch of space-time they cover. So in the Churchill, these are the Churchill coordinates. But of course, these circles are not supposed to be circles. This is just my drawing, is pictorial drawing up here. And we know that the outer horizon, the horizon that I'm talking about up here, in the asymptotic region, there is this outer horizon. So this is scry. You look at past of scry, you look at the boundary of that region, that is a horizon. That horizon I have written here as r equal to r plus. Now in Schwarzschild space-time, as we saw last time, the Killing vector field, which is time translation at infinity, remains time-like until it comes to the horizon, where it becomes null. But here, in fact, as we saw last time, the Killing vector field, in fact, becomes null earlier. So this is the horizon, but the Killing vector field becomes null already at r is equal to n plus square root of m squared minus a squared cos squared theta. When theta is equal to 0, this term goes away, the two meet, the horizon meet. But for non-zero values of theta, this sphere at any instant of time t, t equal to constant, this is sphere, and the statement is that topological sphere, and then the statement is that is where the Killing vector field becomes null. So that is our now the infinite redshift vector. And as we saw last time, we got the Killing vector fields Ta and phi a, and we got this locally non-rotating vector field, which is Ta minus or zero angular momentum, almost zero angular momentum observer field, zero angular momentum observers, T dot phi 1 phi dot 5. That's 5. This is the vector field up here. And this vector field, as we saw, we can check explicitly, it remains time-like all the way up to the horizon. So this vector field is time-like now, up to the horizon. In the asymptotic region, it is time-like, and it remains time-like all the way up to the horizon. And therefore, there is this in-between region between the ergosphere, so it's a sphere, and the horizon, where the Killing vector field here, the time translated to infinity, is space-like. So the Killing vector field up here is space-like, which means that the conserved energy defined by the Killing vector field here can be of any sign. It can be positive or negative. So remember that for particles, for massive particles with 4 velocity u, the energy is just given a minus UATA, you can use the time translation, and at infinity, well, no problem. This is exactly what we would say energy is in Minkowski space-time. And then the angular momentum will be given by UA, UA5. Okay, and now what happens is that in the region where this is time-like, asymptotic region, where PA is time-like, this is the inner U is always time-like by definition. It's a 4 velocity, and it is so UA is equal to -1. It is always time-like. So therefore, we got an inner product at infinity. We got an inner product between 2 time-like vectors. Inner product between any 2 time-like vectors is negative, with our signature minus plus plus plus, and therefore this is always a positive quantity. So asymptotic region, this is the case. Therefore, P is positive. But once, and even on the ergosphere, T dot T is equal to 0, but it is a future-directed null vector. Again, the inner product between a future-directed null vector and a future-directed time-like vector is always negative. Therefore, the energy is always positive. But for space-like vectors, the energy can be either side. For example, supposing this is a d by dt vector field up here, and I can take a space-like vector, which is a linear combination of t and say x vector field. So t plus 3 times x. So that will be actually a space-like vector field. Or I can take t times, so I'll get some vector field like a vector like that. Or I can take t minus, so here is t, and I can take a space-like vector, so this null cone up here. So space-like vector t plus alpha x, where alpha is bigger than 1. Or I can take here t minus alpha x. Okay, so alpha is positive bigger than 1. And then the statement is that the inner product between xa, which is actually a space-like vector, unit space-like vector, with this will be positive, will be alpha. With this will be negative, which will be minus alpha. So it can be any sign. And if in fact the space-like vector is in the y direction, then the inner product will just be 0. So the inner product between space-like vectors have this property. So the inner product between space-like vector and time-like vector has a property that it can have any sign. And that is why here we have a region where the energy can be actually any sign. In the ergo region, energy is any sign. Energy is already of any sign up here. So you can envisage a process in which a particle comes in from infinity. So supposing it's, so this is a space like this is a space diagram of the particle coming in from infinity, because it's all a space picture, and instead of time, it's a space picture. I'm projecting it at some instant of time. So this is a trajectory up here. It comes in at infinity, and then supposing this particle is a radioactive particle and it decays into 2 particles. Of course, in the process, the energy and angular momentum, they are the Killing vector fields, so they will be conserved. So I get one particle coming in and it decays into two particles, and therefore, and supposing one of them actually falls into the black hole, into the horizon, and the other one goes out to infinity. Then you can see that the energy of this particle, which is falling in, so this is a particle, let's suppose particle A, particle B falls in, particle C comes out. So the energy of A is of course positive, there's no problem. But I could arrange so that the energy of B is actually negative, because I mean, supposing it happens that the energy of B is negative, it decays, because time-like vectors with inner product which is positive with respect to UA are allowed, and energy is minus the inner product, so the energy could be negative. So suppose it happens that EB is negative, then it follows immediately that EC, energy is conserved, so this energy was coming in here, and some negative energy went in, that means the energy that comes out would be bigger than the original energy. So then that follows immediately that energy of the particle EC will be bigger than the energy of the particle. So this is called the Penrose process. Penrose realized it very quickly after the geometry of space-time became clear. And this is a way of extracting energy out of the black hole. And so, in fact, Misner Thornwheeler had this little cartoon saying that a future civilization could just use a black hole. They could take their garbage and they could throw the garbage into the ergo region and get rid of the garbage, and at the same time arrange so that part of the garbage carries negative energy and something comes out, and that whatever comes out would actually have greater energy. So this would be a way of getting energy out of the black hole. So at first it sounds crazy, because it sounds like, well, how can it be? Because somehow the total energy should be conserved, you're getting something out of nothing. Of course, what is happening is that as the particles fall into the horizon, then in fact their energy is negative, and it follows as follows, and this I can leave it as an exercise for you to do. This in fact could be a part of your extra credit problem in the last homework, trying to understand the energetics of that process. So what you use the fact that this vector field alpha is actually null and future directed. At the horizon, and of course it's future directed because it was future directed and time-like in the neighborhood here, therefore it's future directed. So it's future directed and then time-like up here, null up here, and therefore it follows that alpha A UA is negative. UA is future directed time-like, alpha is future directed null, and therefore UA alpha A, inner product is always negative. Use this fact, and use the fact that suppose the particle, so this is a B particle if you like, so UA take UA to be the force velocity of the B particle. Use this fact up here, and then suppose B actually carries negative energy. Suppose UA is positive at the horizon. So this B particle falls in to the black hole, and at the horizon, of course, its forward velocity is going to be its time-lag, and forward velocity is normalized. The fact that it's time-lag is important. Normalization is not that important because we're just looking at science at the moment. And then, supposing in fact this particle is carrying negative energy as it falls to the black hole, then you can show that it carries negative angular momentum. So the particle falls to the black hole and carries negative energy, therefore it's reducing its mass. which is also reducing the angular momentum necessarily. This is what this one says. And so where is the energy coming from? The energy is coming from the rotational energy of the black hole. The black hole is not rotating as fast as it did before the particle fell in. It slowed down a little bit. Therefore, it's kind of the rotational, heuristically, the rotational energy of the black hole has been reduced a little bit, and that is the energy that is extracted out at infinity. So you dump in negative angular momentum, then at some stage the black hole is, keep doing it. Then at some stage the black hole actually is not going to be rotating anymore. I mean, the question that you want to ask is, oh, that's great. I just found one rotating black hole and I have an infinite source of energy. I just throw in these particles, the negative energy falls in, positive energy goes up. But notice what happens. As the angular momentum of this black hole shrinks, so therefore A parameter actually decreases up here. So therefore, as A decreases, this term goes away, this term goes away. That means that the ergo region is in between up here, is actually shrinking. So therefore, as the angular momentum is decreasing, the ergosphere and the horizon will coincide, because of course, as the angular momentum decreases, in the limit, you will just get the Schwarzschild black hole. And for the Schwarzschild black hole, the T dot phi is 0, therefore T and alpha are the same. The Killing vector field remains time-like until here. And therefore, in Schwarzschild black hole, we don't have this Penrose process, because the Killing vector field is time-like all the way up to the horizon. So the energy of the particle is going to be always positive. Even if this were a Schwarzschild black hole, even if I throw in a particle and it decays radioactively, even the particle which is actually falling into the black hole will always carry positive energy. Because of the horizon, the Killing vector field is still future directed and null, but future directed. Therefore, the particle will always carry positive energy into the black hole up here. So what is happening is that in the Kerr space-time, I arrange this carefully, and the detailed kinematics has to be worked out to make sure that you can arrange it carefully. The particle actually does fall into the black hole, etc. But you can do that. And then when that is done, what you can see is that the black hole is actually, its mass is reduced, but its angular momentum is also reduced. Mass is reduced is fine, right? Because we might say, okay, mass is reduced, and I'm getting mass out up here. So naively at first it would seem that I can get out as much energy as the mass of the black hole. But that is not the case. I'm actually shrinking the black hole, but I'm also slowing it down. And once the mass becomes equal to angular momentum, this region has disappeared and Penrose process is no longer viable. So what happens? What is this endpoint state, so to say, the Schwarzschild black hole that I would get? So black hole slows down, a black hole angular momentum decreases. And as the black hole angular momentum decreases, you find that therefore it tends to, the process can continue in principle until you get to Schwarzschild black hole. Once you are at the Schwarzschild black hole, no ergo region, because at A equals 0, ergosphere is the same as horizon. Ergosphere, where the time-like Killing vector becomes null, the time translation is the same as horizon. Outer horizon, in the short, because it's Schwarzschild black hole, and therefore the process stops. I'm just repeating what I just said before. So the question is, what then is the mass of the Schwarzschild black hole? So what we know is, this I'm parachuting for you, but we're going to see this a little bit in detail, that what happens is that in all these processes, so long as the energy conditions are satisfied by the matter carries only positive energy, it doesn't carry negative energy. I mean, at infinity, in the normal circumstances, it does not carry negative energy. So if in fact, for normal matter, the statement is that we have an area theorem. Which says that in all these processes, you could not decrease the area of the black hole. And so that's the statement up here. So we got this area theorem. Now what is the area? Area is, you have to calculate what the area is. So it will be integral on the two sphere at r equal to RH of square root of the metric, of the two-dimensional metric, times d theta d phi. And you calculate that, and you get this just to be equal to 4 pi r squared plus a squared. R1 is squared plus a squared. So R was a coordinate. So if you like, R squared plus a squared is the proper area. So this is the proper area radius. RH is the coordinate radius in our Boyle-Lindquist coordinates, but this proper radius, you just do this h, square root of h, and just see what you get. You will get that answer up here is equal to that. So therefore, the area cannot decrease in the process. So if the area cannot decrease, and suppose we are at the best possible situation in which area remains constant, so best scenario, it could decrease, but suppose we are the process is as efficient as we want, so that we don't change the area. Then at the end of that process, we're going to Schwarzschild black hole. And for the Schwarzschild black hole, we know that the area is equal to 4 pi times the radius squared, because there the radius is just the, it's a geometrical meaning. R is a geometrical coordinate. 4 pi r squared is really the area of the two spheres, where R is the Schwarzschild R, and R is equal to 2m. So I'll just get here. So I'll get here 16 pi. 16 pi mass. So at the end of the day, that is what is I'm going to obtain. However, in the beginning, therefore, so this is often called so this mass, as we'll see in a minute, of the final black hole is less than the mass of the initial black hole, curved black hole that we started out with. So this m Schwarzschild that will remain at the moment, at the end of here, which is just given by 4 pi times r of the physical curved black hole we started out with, a squared. So this is curved black hole we started out with. So this is the area up here, and that area is equal to 16 pi. Therefore, I can divide by 16 pi up here. So I'll get 1/4. So that is the final the Schwarzschild black hole that will end up with this mass up here. And this, as I was about to say, is actually smaller than the mass of the original black hole that we started out with. So the statement is that we start with m is bigger than m Schwarzschild that we end up with. So sometimes this is called the irreducible mass of the black hole. In other words, that is a mass you cannot, by Penrose process, by slowing down the process or whatever it is, you cannot really decrease its mass. And intuitively, the statement is that the difference between the two is coming because of the rotation energy of the black hole. There are explicit inequalities which tell you these various facts, but I think at the moment, unless you're working on a specific problem, you don't have to know the detailed algebra. Just 1 second, there's another question.
So what assures that this is an adiabatic process that slowly gets you to Schwarzschild? I might arrange it such that when its rotation is still something, I dump angular momentum to make its final state with negative angular momentum, meaning it is spinning the other way around, and still create a GO region, and I can keep on doing that. What assures What part of the theorem assures that?
Okay, so then the mass would increase again. So the mass of that black hole would be bigger than the irreducible mass.
No,
The mass of any black hole which is rotating would be bigger than the irreducible mass in the process.
Right, so somehow I won't be able to extract energy in that.
Yeah, so that's why I said this is the best scenario. This is the maximum energy you extract in this
So
way.
what really happens then is that yes, I might be able to dump in, arrange things such that I will
Yeah. So
rotate in the opposite direction,
Right.
but that doesn't matter because the mass then keeps on increasing.
mass keeps on increasing, right, exactly. And that's the main thing. I mean, I could, yeah. So I could also increase the, I might say, oh, but I'm going to, first, where the contradiction could come is that I throw these particles so that I actually increase the angular momentum and also decrease the mass. If I could increase the angular momentum, decrease the mass, then I can keep going.
Yes.
But the statement is that this little calculation, which is homework, will tell you that that's not possible. If in fact it's carrying negative angular momentum across the horizon, then it must carry negative energy. You have a question?
So which part does it lead to the conclusion that this area always increases?
Oh, I'm not yet told you yet, right?
Okay.
Yeah, so this is something, there's an independent statement. We have to sort of, I'm just telling you at the moment, just accept that the area cannot decrease, and then this happens. So,
Because if you look at that, I mean, A is increasing, RH is also increasing, I guess.
no,
I mean, decreasing.
little a is decreased.
Yeah, decreasing. So it seems like that it's decreasing.
Right. So the statement is that in this process, what is happening is that, you see what is happening, we see that the R up here, RH, which is the RH up here, R plus is the same as RH up here. You can see that this is really less than 2m, right? This is strictly less than 2m.
Yeah.
Okay. So the statement up here is that the relation between RH is not a function of just m, or it's not a function of, it's not that RH is a function of m and this is a, and the two things are going high. RH is also, so there's a dependence here as well. So therefore, and we're going to see this now.
I think that what is happening in the horizon, the inner thing is expanding.
Yeah.
And that is what is happening in that.
Yeah, the inner thing is expanding and the outer thing is. Okay. All right. Any other questions? All right. So this is the Penrose process. And now, I mean, the thing is that this was conceptually the deep idea, but on the other hand, in actual practice, there are not going to be that many particles and so on falling in. But what we can do is, we can do the same thing with fields. I was going to do a little bit more detail, but time runs out, so let's not do it in too many detail. So what happens is the following. I can take the curved space-time, and the curved space-time, I can have matter fields, a test field, to begin with. So this matter field will satisfy, so I'm not coupling it back to the space-time geometry, just like these particles we're thinking about, we have test particles, and we're not coupling it back. We bring in back a reaction at the end by conservation law, saying that, well, if the energy is coming out, and the angular momentum is negative angular momentum is going in, then that means the black hole must be both losing mass and angular momentum. At the end, we say that. But to begin with, we're just looking at test fields, test particles. Similarly here, we look at test field. I mean, what we should really do is to have coupled system, right, of Einstein and Klein-Gordon, or Einstein and Maxwell equations, and you throw in the Maxwell fields and see what happens. And such rigorous, you can do it numerically, or you can do it, rigorous theorems can be proved along those lines, but they had generally been, the rigorous theorem had generally been proved only for the charged Schwarzschild or Reissner-Nosdorf black hole, which has very similar structure as a Kerr black hole. So at the moment, what we're going to do is looking at this process in which we take Kerr spacetime and we look at test fields. Okay. So when we look at test fields for this Kerr spacetime, then so for example, you look at block of phi, which is just GAB gonna be a phi equals 0. You look at this thing up here, this test equation, this wave equation, or you can do Maxwell's equation. Or if you like the curve of star f equal to 0, we can look at the Maxwell's equation. And we saw before that we can define a constant quantity called energy, which is given by TAB times the killing vector times the unit normal to the surface, 3 surface, times d3v. And that was the energy of a field. And similarly, we got the notion of angular momentum. So, we got notion of angular momentum. So this is a constant energy. And the point is that if in fact stress energy tensor, if it is normal matter, and this is the case, if I have triangular field or if I have the Maxwell field, for normal matter the stress energy tensor satisfies energy conditions, which means in particular that if I got TAB times 2 time-like vectors, TA and B, if they are both time-like, then this quantity is positive. Okay, this quantity cannot be it's actually strictly possible positive and 0 if only TAB itself is 0. But so let me just write down that. So if the energy condition is satisfied not by normal method, you can see that energy density up here is positive. You're integrating this, therefore the total energy will be positive, right? There's no problem about that. And that is generally the energy is positive. But now T is not positive everywhere because in this ergo region, T becomes negative. Therefore the total energy does not have to be positive. Because the total energy does not have to be positive, I can throw in again waves from infinity, which of course carry positive energy, but I can arrange, and you can write down exactly what happens to those waves. So, and some of them can fall in, and those which fall in with negative angular momentum across the horizon, the flux of the angular momentum across the horizon is negative, they will come out with greater energy out at infinity. So again, it's a scattering problem in which there is a black hole, like this camera is a black hole, and we're sending some waves, right? I'm creating some waves and throwing at the thing, and then the statement is that something comes out on the other side. So some of it is absorbed, some of it is coming out, and the statement is that for certain modes of the field, the energy that comes out is bigger than the energy that is sent in. Of course, for a generic mode, it's not the case. So you'll have to arrange carefully, sending in only a wave packet of certain modes of the field, so that this happens. And by modes, I just mean we have the wave function phi, not wave function, the field phi. You can expand it out because we have got 2 killing vector fields. You see, in general, in curved spacetimes, you cannot do Fourier decomposition. But if I got a killing symmetry, then you can do the Fourier decomposition with respect to the parameter, affine parameter of the killing vector field. So therefore, we can look for solutions e to the I omega t times e to the I m phi, and then you will have some function of r and theta. And in curved spacetime, in fact, you can separate the variables. That's how you can actually separate the variables. So therefore, this is just depends on m and omega and n and m and omega. And then this R and S actually satisfy certain differential equations. And now the statement is that actually you don't have to worry about what the differential equation is that is satisfied by S. But the equation satisfied by R is important. So I could write it down, but I mean it's also in the books, and so you're not going to learn too much by looking at just the equation up here. So therefore, look at the radial equation. It's a second order equation. And look at the radial equation and put boundary condition that the wave is ingoing at the horizon. the mode is ingoing at the horizon and outgoing at infinity. So these are the boundary conditions put on individual modes. But of course, if I superpose those modes and construct a wave packet, then since each mode satisfies this boundary condition, the wave packet will also satisfy this boundary condition. So I got a wave packet which is falling into the horizon, at the horizon is falling in, and at infinity is going out. So we just put those boundary conditions and we solve the equation. And then we get experiential solutions. And then what you see is that in fact, again, it's a very similar argument up here. Again, the waves which are actually carrying in negative energy will necessarily carry negative angular momentum. It's the same kind of argument up here. You have to just calculate the flux of energy and the flux of angular momentum falling across the horizon, and that is just obtained by this quantity evaluated at the horizon. That will be the flux up here, so you can calculate that quantity up here. And what you find is that in fact, if in fact 0 is less than omega, sorry, I don't have it here. So there is an inequality. 0 is less than, so omega is positive, but omega is less than something, which is that something up here, which is built out of some function, which is built out of the horizon and the total angular momentum. If in fact omega is in that region, so that is the same as m here, because the angular momentum carried by the wave is given by m up here. Then the statement is that, and then h, mass of the black hole. Then the statement is that then we got more energy coming out. That is to say, we can have super radiance. So the statement is that there is a range of omega for each value of the angular momentum. There is a range of omega for which, if you construct the wave packet with those frequencies and those angular momentum m values, then in fact more energy will come out at infinity than what is falling in. Again, this is one of the possible project or possible subjects for the term paper. Those of you are taking the class for credit, you can look at it. Again, the web page does have announcements now, and there is an announcement which is explicitly for term papers. And as we go along, I will add more and more ideas. Please read what is expected of the term paper, which is on that web page. So we got this interesting ideas up here, that namely that we got this phenomena in presence of black holes, and these phenomena turn out to be astrophysically important. It's not just a mathematical curiosity; they turn out to be astrophysically important. Yeah.
You said when I put negative energy in, I also have to put negative angular momentum, right? What about the other way around? Are they always bounded together, or can I put negative angular momentum and positive energy in?
Yeah, you could put negative angular momentum and positive energy, depending on that. Okay. So as we see, there's a fascinating interplay, right? I mean, who would have thought, right? That here is Riemann talking about Riemannian geometry. In fact, space may not be flat, space may be curved and all that. And then Einstein comes and says, yes, in fact, space is curved. And in fact, you have got this Einstein's equation, and gravity is really encoded in the geometry of space and time. And then these curvature effects create all these incredible physical phenomena which could not be dreamt of before general relativity, where geometry was inert, was given once and for all. So this really is very dramatic physical effects coming out of geometry. So that is the end of this topic up here. And then the next topic I want to spend just a few minutes on is really issue of uniqueness. What I want to explain is the following. You might say, okay, you saw Schwarzschild space-time, it was simplest, expected symmetric. You saw one axis symmetric space-time, which is curved. Why are you spending all this time on these two planes? Why is the literature, why so much work analytically, I would say 99% of the work is done on either Kerr black hole and Schwarzschild black hole and their perturbations on that. And that is what the whole thing is usually done. So one would say, well, why? I mean, they're just two solutions. Why are you taking it so seriously? And that is what I'm trying to answer now. But are there any questions about anything we have done so far about Kerr, Schwarzschild, etc.? Because this is the end of the stage of the Kerr and Schwarzschild part. Okay, so uniqueness. The reason why these solutions are important is something that is totally unexpected again. We would not have anticipated this. I mentioned this in the very first lecture, which was in Osmond, that if you take stars, right, say for example static star, non-rotating star up here, they are not spherical. I mean, they can be oblate, they can be prolate. There are a lot of structure to it. But it turns out, as I mentioned already in the first lecture, very quickly, that if you have a non-rotating black hole, it must be spherically symmetric. So this really is a big surprise, not at all something that was expected. Non-rotating black hole, non-rotating. I misspoke, I meant non-rotating stationary black hole, time independent. And if it is non-rotating, then the vector field is hypersurface orthogonal, and then it is static. So let me just write down here once and for all. Static just means we have a Killing vector field, which is time-like at infinity, and is hypersurface orthogonal. And such spacetimes have no angular momentum, because the angular momentum is directly related to the twist of the Killing vector field that we introduced last time. And more generally, we just have stationary solutions. So there is a Killing vector field, which is time-like at infinity, and not hypersurface orthogonal in general. I mean, generally, of course, every static solution is also stationary, but one says that if it is not static, then one calls it stationary, right? In other words, if it is not hypersurface orthogonal, then it is stationary. If you want a very simple image, then a lake, which is peaceful, no wind or anything, is static. A river is stationary. It's not if you look at the river at any cross section, it's always the same, but it's clearly something is happening there. So that is stationary up here. So Kerr is this is like a lake, and this is like a river up here. Or I told you about these vector fields. Here, these vector fields out at infinity, they look hypersurface orthogonal, but they're never exactly hypersurface orthogonal. As you come in, you see that in fact there is a rotation in them for stationary spacetimes. So non-rotating, so that is to say static black holes are necessarily spherically symmetric. They are necessarily spherically symmetric. And because of Birkhoff's theorem, then they are Schwarzschild. So this is a theorem which was first proved by Israel, I think in 67, 68, a couple of papers, and then improved by others, several people. I think this also is a good topic for term papers if anybody wants to do it. And there is a standard reference for that, is really a Living Reviews article. It is also on the archives, but you can just look for Living Reviews. It is, and look at the articles. And this Living Reviews is a Relativity. It is a journal. It's called Living Reviews because they are review articles. but the authors are invited every few years to go and update it. That's why it's a living review. So living reviews article, and that is by Khrushchev and Costa. João Costa and Piotr Khrushchev. You'll see all the fine details. I'm really not doing justice to it at all, but just doing it in 10 minutes. But that's I think we're covering so many diverse topics in this course that we cannot spend much more time on this topic. What is important is that you understand what the structure is, and then you can go and plunge into literature if you want to use something somewhere. So the structure is that non-rotating or static black holes are necessarily spherical symmetric, and therefore, in fact, it's Schwarzschild. So I can have these oblate and the prolate stars, but I cannot have an oblate and prolate black hole, which is, by black hole I mean black holes, we mean vacuum solutions. So they're completely vacuum and with any event horizon. So it's very surprising that this is the case, right? So stars come in many forms, but black holes don't come in many forms. If it's not rotating, then it must be spherical. And again, I mentioned this in the very first lecture, that when the result first came out, this was before my time, but people tell me, that when the result first came out, people were very surprised, and people thought that means that black holes are very rare. Because the argument was that there's almost no star which is exactly spherical, and therefore if a star actually, regular star, which like sun is not spherical, so if it were to collapse, then the statement is that it has all these multiple moments, and it cannot possibly go to perfectly symmetric, spherically symmetric black holes. But Penrose was one person who took the courageous stand at that time, based on his intuition, to argue forcefully the other way around. They said, no, black holes in fact will form generically. What will happen is that the star has all these multiple moments, because its shape has these various multiple moments, and those multiple moments will be radiated away by gravitational waves, or by gravitational waves, as the star actually collapses up here, if it is purely vacuum process. So the Penrose's idea would be that the multiple moments that generic collapse, generic stars, which are not spherically symmetric, will give rise to a black hole upon collapse. I say full collapse because if the mass is not large enough that we know that they could become neutron stars, for example, or white dwarfs, because then the Fermi degeneracy pressure can hold together, can balance the gravitational attraction and make them in equilibrium. But if the mass is very large, then in fact they collapse. And the statement is that they will give rise to a black hole by radiating away higher moments. And this is kind of the quality picture that we have had since then. This was a few years later proved by Price, Richard Price, in the linearized theory, linearized approximation. So perturbations of Schwarzschild in the linear approximation. And in the full nonlinear case, this issue really has been investigated relatively recently by people like the Formos and Rodyansky at Princeton. So they are looking at full nonlinear general relativity. They're looking at some data which is not spherically symmetric and which will collapse. Of course, on a computer you can just do it, but proving general theorems has really been done in terms of this radiating away the higher multiple moments has been done only recently.
So Penrose did not take the next step of computing the quasi-dominant moments?
Oh no.
Why would that?
He's not an astrophysicist, I mean, really in his heart, right?
I mean, he just proved that, they will radiate away angular moments in the form of gravitational waves.
He did not prove it.
Oh, he just said that.
He just claimed that.
Oh, he just-
and it was really Richard Price who actually did
That's right.
really
That
write
is
the
Price's
approximation
work,
there.
I know.
I think the importance of quasi-normal modes, or even the notion of quasi-normal modes, was not widely known at the time. For example, when people like Vishweshwara studied the stability of this black hole, this whole importance and thing. I don't know, I don't recall the history explicitly, but I remember that Chandra was one person, because he came from really astrophysics, and where in those cases quasi-normal modes were very important, and that they made them. I mean, where people like Ben Schmidt and particularly Ben Schmidt and his collaborators had actually mathematically understood what quasi-normal modes mean in this context and what happened, but their importance was really brought to forefront by Chandrasekhar only. So it was quite it was almost 20 years later.
So Penrose's was only a conjecture. It did not really.
Oh, it was like, the intuition. It was really, that's why, that is the point about intuition, right? I mean, that is the whole, people who have this great thing that goes completely counter to the culture and turn out to be right, their intuition is really what drives the whole fields very often, right? Of course, it has to be substantiated by some work, but he could have been wrong, but he wasn't.
Do you think there was any other work before Vishnu's first paper on?
No, I don't think so.
quasi-normal?
I don't think we should read quasi-normal mode. He just looked at
No, he did the scattering.
the e to the I omega t. So the not necessarily the complex frequency. In fact, he was looking at you're showing that with these boundary conditions, there are no complex frequencies. That is why you are saying that it is actually stable. So you're not putting the boundary conditions that are needed for the quasi-normal mode. So that is the key point. That you was putting the boundary conditions that I was putting there up here. Okay. So these are non-rotating black holes. So this is why Schwarzschild is so important, right? Because when the black hole is actually formed, right, then when it settles down ultimately, the idea is that that black hole would actually be a static black hole. And that because it's settled, if it's not rotating, it will be. And then there's only one equilibrium position, equilibrium configuration, and that is the Schwarzschild black hole. And that is why it is a final equilibrium configuration, and that is why it is so important. And then for the rotating black holes, again the statement is the following. Okay, for rotating black hole. So supposing I got a stationary black hole, then what we would like to prove is that that stationary black hole is curved. There's no obvious reason for this to be true. I should also say here one thing before going to curve, namely, people are all familiar with Birkhoff's theorem. Birkhoff's theorem doesn't have to do with black holes. It's a local theorem. It doesn't have to do with global boundary conditions. It just says that if you have a spherically symmetric solution of Einstein's equation, then Schwarzschild. So it is saying that spherical symmetry implies staticity. Okay. So Birkhoff theorem. So here I just put on the side of here. This Birkhoff theorem is local theorem. That's why it was proved a long time ago. And it says that vacuum equation plus spherical symmetry then it is static, then it is Schwarzschild, and therefore static. And therefore, yeah. The theorem we're talking about is opposite. It says that it is static. The theorem we're talking about here is not a local theorem. It has to be a black hole. There are global assumptions about the boundary conditions, particularly what happens at the horizon. So this theorem is global theorem. It's not local theorem. It assumes vacuum equations. It assumes staticity, and then concludes that it should be spherical symmetry. So it's opposite of Birkhoff's theorem. So please remember that. It's not, don't confuse Birkhoff's theorem. Okay, let's come back to the rotating black holes. And we got, so in this case, stationary black hole. And the gist is that, indeed, if you have stationary black holes, then that is called a curved solution. But the situation is not as clean in this case. So let me tell you, therefore, what is known and what is not known. So first thing is to say that supposing it is stationary, then the thing is that there is an additional killing field, which of course you want to think is the rotational killing field. And I think to prove that the additional killing field should exist at the horizon is fine. There's no problem with that. But then what we want to show is that in fact that additional killing field actually extends out all the way to infinity. It's global. It's not just near the horizon or at the horizon. It's not just the horizon is axisymmetric, but the space-time is axisymmetric. And here, Hawking had an argument which in the middle of the proof had some physical thing about it. Supposing I drop in particle, then something will happen and so on. So it's not a proof, right? And then after that, it was shown that in fact if you assume the space-time metric is analytic, right? C omega, not C infinity, but C omega, then if you have a killing vector field in some neighborhood, then you have got this killing vector field everywhere. But analyticity is a very strong assumption, right? If you give me an analytical function in this little neighborhood here, in this cup, or half a cup, or 1/10 of a cup, 1/100th of a cup, if you give me the analytic function there, I know what it is everywhere, because the Taylor's expansion converges. Therefore, I know it everywhere here. So analyticity, most mathematicians tend to feel, is too strong an assumption for any physical reason. And nobody, so at first one was like, yeah, but it's always the case. You first prove it for analytical category, and then you generalize it. That's what happened, for example, with the existence uniqueness theorem of differential equations. First, they were established for analytic initial data, and then the solution exists, and of course again analytic, etc. And then eventually it was done for lower differentiability, C2, even distributional, and so on. The techniques are much more complicated. Now they involve various kind of function spaces, which were not necessary for the analytic proof, but it was done. So I think one's first reaction is, yeah, it's analyticity. Yes, that's right. I mean, that's a technical assumption one has to remove. One has to remove, and one will remove it. But it has been since 70s, right? So 50 years almost, right? I mean, not quite, but 40 plus years have passed, and nobody has been able to remove it. So there's an additional killing field, and this depends on the analyticity assumptions. And most mathematicians don't find that this is satisfactory, and they feel that one should be able to do better. But let's suppose that in fact it is stationary and axisymmetric. Supposing it is stationary and axisymmetric, then there are nice proofs to say that then it's curve. Of course, this is all assuming vacuum equation. If there are electromagnetic fields, then you get Kerr-Newman, the other things that you get. So this is the situation that we have got. And again, it could be, we might be surprised. I think the probability is very low. But on the other hand, it is not zero. That one of you actually shows that in fact there is a stationary solution, which is a black hole, which is not axisymmetric. Too bad, it's just not axisymmetric. That's life. It's not ruled out. So I really want to encourage you. I want to encourage you especially because this last part of the theorem was proved by two students completely independently. One in Poland and one in Australia. The last part of the theorem, so last part here, was proved by graduate students, who were graduate students at the time, was Mazur in Poland, in Krakow, and Bunting in Australia. I think I believe, but I'm not sure. And they were really graduate students. So, I mean, there are no good ideas. People have tried to look for such solutions, It's not so easy to find solutions which are regular horizon, asymptotically flat, and so on. But it's not ruled out. Yeah. Now, I mean, to me, this whole uniqueness theorem is very interesting. I mean, so even if we just suppose the stationary axis is symmetric, then it's unique. This is here, it is unique, completely non-rotating black holes, it is unique. It's all very simple. And to me, this is fascinating, not only because stars come in infinite varieties, stationary stars, static stars come in infinite varieties, whereas black holes can't. That already is something that is pretty surprising, and But in addition to that, something that is funny is that these theorems hold only 4 dimensions. That is to say, uniqueness does not hold in higher dimensions. There are other kinds of black holes in higher dimensions. And even in 4 dimensions, uniqueness holds only for Einstein Maxwell fields. But if you bring in other matter fields, such as if you include Yang-Mills fields, so non-abelian Yang-Mills fields, or various scalar fields coupled to the non-abelian Yang-Mills fields. These have various names. Again, we won't go into details about them. Sometimes there are ginetons, Higgs, skyrmions. So these theories are understood. They are microscopically interesting, important. But if you include such fields, then uniqueness fails. There are more solutions. That is to say, the solutions are no longer characterized by mass, angular momentum, and charges defined at infinity. Now, finding such solution was a cottage industry at the time. People looked at it very much, and they tried to find them, and so on and so forth. And there are lots of such solutions, lots of families of such solutions. So it's kind of a wonderful thing, right? I mean, none of these things are going to be non-linear in nature. Nature could have been different, and there could have been non-abelian Yang-Mills fields all around us, just as there are Maxwell fields. They're just propagating, We could have these tube lights with Yang-Mills fields instead of photons, abelian photons. But in nature, Yang-Mills fields are all confined. They are very short range. They are just inside the particles, right? I mean, they're not. In nature, Yang-Mills fields happen to exist only in the confined phase. They don't exist in this non-linear. There are no macroscopic, long-range Yang-Mills fields in nature. If they had been there, then Kerr solution would not have been that interesting in some ways, because such solutions were. But the statement is that so none of these things have long-range forces. The only long-range forces are electromagnetism and gravity, and for them, there's uniqueness. I mean, to me, it sort of sounds almost mystical, magical, right? That it is only in 4 space-time dimension. It's only for these fields that are physically relevant for black holes. So that is the statement. Yeah.
So what could happen is inside a neutron star core, could you have a quark-gluon plasma or something like that, where fields could be long-range?
Right. So
I
the
mean,
question.
even there is not long range, but what I mean is the quarks exist in unconfined.
Right. So I think what we want here is that these fields which go out to infinity, right? I mean, like one upon
So you do
R,
want
so
to
to
know
say,
that,
something
yeah.
like that. So that's what I think one long range thing.
That is true, but what I'm asking is whether or not somehow, you know about these spontaneous scalarization and things like that that has been talked about, whether or not some process could occur which could, inside neutron stars, which could violate one of these conditions. Meaning,
So I mean, solutions will exist, but these solutions mean that these fields go out all the way to infinity, right? That's what this is. So therefore, the statement is that those are not going out all the way to infinity. They don't have charges defined at infinity. Those are just zero charges at infinity. Okay. But the statement that you are asking is perhaps that, well, could there be these black holes which are this, you know, with the, yeah, that's a question you're really asking. Could it happen that you have got these black holes which have some internal charges, right? Which belong to this family,
Yeah.
and
we will
but beyond what they are talking about, because they are really talking about, when they say Young mills, they mean it's really not in confined phase. They really mean Young mills. So it really is beyond this, the analysis that these people have done to find these solutions. In other words, the analysis that is done up here does not incorporate the confined phase. Right? So, but supposing in fact there existed some analogous theorem, supposing, you know, for the confined phase. So what would happen? Well, all these solutions turn out, it's widely believed, and wherever it was, I had to stop in 1 minute, wherever it is actually done in the detail, it has been confirmed that all these solutions are unstable. So there are black holes, they're stationary, but they're unstable. And that is why we don't take them too seriously anyway. There are two reasons. One is that the assumptions of the theorem don't allow the realistic processes that will happen inside the neutron star, and furthermore, these solutions are unstable. So it looks like fantastic thing, and okay, we go home. And in fact, people like Martin Rees have said explicitly, he's a god, right? Martin Rees in astrophysics. And he said explicitly that, well, in the 60s and 70s, okay, in the 70s, Hawking and others laid down the foundations of black hole physics, and after that, we're just doing engineering. We're just applying that theory, and there's nothing, and all the fundamental problems are solved. But we'll see tomorrow, next time. I hope that, as usual, I always think I can do more than I can in a class. Next time we'll see that, in fact, that's not true. We know almost nothing about dynamical black holes. These are all stationary black holes. Realistic black holes that these guys see are not stationary black holes. The end point is stationary, but there's a dynamical thing that happens between, and none of these theorems apply there. So next time we'll talk about the limitations of this whole framework and why we need to go beyond it. And then we'll do what we know about going beyond stationary black holes.